Okay, so let's get started. So so like I said, we're going to go through rate, equilibrium, thermodynamics, acids and bases, redox as well, because I think that's really important. So we're going to start off with rate calculations. So I'm going to put the recording on my YouTube, so you can just watch it on YouTube whenever you want. Okay, so we've got bromine Br2 can be produced by the reaction. Now, when reading a question, a lot of students really struggle with how to actually approach the question. I think that's a really big thing. Like, you could practice rate, but you're like, how on earth is this? Am I going to do this because it's information overload? So with typical like rate questions or typical like topics, they throw things in that are red and herrings, sorry. So they've given us an equation here for the reaction. I always say, like, if they've given you a general equation, it's a red herring. The only equation you should really care about that they've given you is the rate equation. In this case, they haven't given us it. So I always say, like, you don't even need to use this equation in this instance, okay? So they said the student investigates the rate of this reaction by carrying out 4 experiments at the same temperature. The student results are shown below. Okay, explain the reaction orders that can be determined from the student's results. Determine the rate equation and rate constant for this reaction. Okay, first off, how do you guys feel about questions like these? Do you hate them, or do you feel like kind of do them? You can put like, you're all right with them in the chat. Okay, right. Cool, that's good. I'm glad that you guys like them. Okay, so some of you don't. What I'm going to do is, it's a bit of a mixed bag, is that I'm going to kind of go through the question step by step with you and then ask you guys to kind of like put maybe bit by bit, maybe some answers in the chat, and we'll go from there. Okay, so first things first, what you're going to do when you approach any exam question that is like fat, I'm going to basically write myself a checklist of what they expect me to do. So in this case, this question is a 6 marker. So I always like to do a checklist of what they're expecting me to do. So they want me to do orders. They want me to then work out the rate equation. I'm just going to put equation there. They want me to give them K, and it doesn't say, this is the thing with rate, you have to give the units regardless. Now, have they told me that I have to give them the units? No. But with rate and all of the constants, give units, okay? They don't ask for them, but it's literally a waste of the mark if you don't give it. So always just get used to giving them, okay? Because that is like worth a mark. So out of the, we've got a checklist of 4, and the first, because there's 3 like concentrations, that's 3 marks, and the rest are 3, so that's 6. So that's your checklist. That's what you need to do to get all the marks, okay? So let's do the orders. So first things first, when approaching this question, I'm going to start with bromine minus as a concentration. Don't be awkward. Like, don't like pick like 1 to 4 as an experiment. I always pick like I'm very like regimented. So from the start, I'd pick 1 and 2. Why did I pick 1 and 2 is because it's the closest, but also if you look on the next one, right, BR003 minus, do you see how the concentrations for experiment 1 and 2 are the same? That is a red flag. You don't want to use them if they're the same, so you just skip them, which I'll explain when we get to it. So that's kind of why, what comes to your thought process of what experiment do I actually use and why, okay? But in this case, I've got a difference between 1 and 2, and you want a difference to be able to work out essentially the order. So that's why I've picked 1 and 2. So for BR minus, I'm going to do experiments 1 and to 2. You need to literally write that down, what experiments you're looking at, because they've said explain how the student's results. So you can't just write it out. You literally need to be really, really specific. So with that in case, can you guys work out the difference between experiments 1 and 2 for me? And then drop your answer in the chat. That was quick. You guys are quick. Well done. Okay, yeah. So if you didn't know how to do that, you just do 6 times 10 to the power minus 2 divided by 2 times 10 to the power minus 2, and then you should get a difference of 3. Okay, perfect. That is what you do. Then the whole point of rate and the rate equation is you want to see how the concentration of these ions impact the rate. So if you're going to have a look at the difference between the rate and how that concentration has impacted the rate. So can you guys do the differences in experiments 1 to 2 for the rate as well? Perfect. Okay. So if you didn't know how to do that, you just do 7.56 times 10 to the power minus 4 divided by 2.52 times 10 to the power minus 4, okay? That will give you 3. So what is the order if they're the same? Perfect. Yeah, first order. Really good. Okay, that's done. We've got 1 mark. So then we've got to work out the next one. So it's a bit harder from this point on. And this is where people get confused, okay? So same things. I'm going to compare experiments 1 to 3. I kind of explained why, but if you look at 1 to 2, there's no difference between them, is there? So I'm going to go from 1 to 3, and that's why I chose that, okay? So with 1 to 3, if I do it in a different color, that would help, actually. Do you see how there's no difference between the rate for 1 to 3, right? They're both the same number, okay? So there's no effect on BRO3 for the rate yet, okay? So I'm going to put rate equals 0 difference. But what is the difference between let's kind of explain it this way. Why do you guys think that there's no effect on the rate with BRO3? You have to kind of look at what we've just worked out as well. If you don't know, just say, tell me in the chat. Okay, this is where it gets difficult. With this, you're not just working out what's on its own, okay? So we've got BR minus, right? And we know that's first order, right? So if we double it, if it's first order, it means if we double BR minus, right? Technically, the rate should double, yeah? But in this case, I want to work out what the difference between BRO3 and what the difference is between experiment 1 and 3. So work out that for me first, and then we'll go a bit further. So what's the difference between 1 and 3 for BRO3 minus? Perfect, 0.5, yeah? So let's write this down. The first one is first order, isn't it? So BR minus is first order. So if I times that by 2, then the rate should be times by 2, isn't it? But BRO3 is having an impact on a rate by a half. So technically, if we're sticking with that, you're doing 2 times by the rate, but then also timesing it by a half, which is what would the answer be? If you do 2 times a half, 1. So what order is it then? First. Does that make sense? Or do you want me to go through that again? Does it make sense? Okay, I'll go through it again. Okay, cool. This is where it gets tricky, guys. So it's fine. So the whole point with rate is you need to see how each individual one impacts the rate. And that's why you get the rate equation. Sometimes you know in the rate equation you have some of the concentration missing. It's because it doesn't have an effect on the rate. Okay. So we have really stupid like evidence. Like it doesn't make any sense when we look at what we're normally doing with BRO3 because we've got a difference of a half here. So we've got a half and a 0 difference here. We need to know why. So the only way that we need to know why is actually what else is actually involved. Well, it's our BR minus. Well, BR minus is first order, which means theoretically, if I times it by 3 or times it by 2, then the rate should do the same thing. So I'm saying we times it by 2. If we times that by 2, that should basically what happened. That's the trend of first order, right? But there's no difference here at all. Why is that the case? Because BRO3 minus is having an effect on the rate at the same time, isn't it? Because these are all 3 things happening at the same time, okay? So if it's a half, if we say we're timesing that by 2 and timesing it by a half at the same time, that's why the rate is 1, like it has no effect because it's being times by 2.5 at the same time. And that's why it's 0 difference. It's just the effect of having the other one as first order. I'm just using times 2 for an example because the base metric for like, it's just the easiest way to describe it. I'm just saying if you times it by 2, then the rate would be times by 2. We're going to talk about H plus we haven't got to yet. Okay. So we'll talk about H plus in a sec, but does that make a bit of sense? Better? Yeah. Okay, right. We're getting there, guys. Okay. This is why I said to you guys, this is a bit of a harder question. So then it gets a bit harder and it gets worse, okay? Don't worry, guys. So let's have a look at the question. So we've got H plus, but again, do you see how there's no changes between 1, 2, 3? First, it's first order, because 2 times a half is 1. It's like we don't do zero order in that sense because it has an effect. It's just only got one of the effect. So if we look at H plus, it's got experiments 1, 2, 3 are the same. Okay, so we're going to compare 1 and 4. Okay, that's where I've done 1 and 4. Okay, is 1 to 4. Okay, so what I want you guys to do with me is give me the difference between 1 and 4. Okay. Okay, and then what the difference for the rate as well? Exactly, it's times by 5, because remember, you got to do 4 times 10 to the power minus 1 divided by 8 times 10 to the power minus 2, you should get 5. Perfect, okay. Now do the rate. Okay. Yeah, 12 and a half. Yeah, perfect. Well done, guys. Okay, so we've got 12 and a half. So we've got our difference for the concentration of H plus is times by 5, and our rate equals 12 and a half. Okay, I don't know why I've done that. Okay, now we need to start theoretically thinking, okay, if it was first order, this would be the effect, or if it's second order, this would be the effect. Okay, if H plus was first order, right, then we would essentially see the rate times by 5, right? Because it'd be 5 times by 5, rate times by 5. Okay, but if we made it second order, because it's technically 5 squared, right? It would be 5 squared then your rate would be times by 25. Does that make sense? That part, what I'm trying to say. If it was second order, yeah, exactly. So if it was second order, it would be 5 squared, which is 25. So your rate should be times by 25, not 12 and a half. Okay, so then our issue is that 12 and a half is between 5 and 25, isn't it? So what do you think? What stupid concentration is going to have is halved it? Which one out of these? Exactly, because it's known to half the rate, isn't it? So half of 25 is 12.5, which means that H plus is actually second order, but the reason why it's not fully showing as second order is because your BRO3 is halving it, and that's why it's disguising it as something else. Does that make sense? Yeah, cool. Happy. I'm happy. Well done, guys. Okay, so we've done the hard parts. We've got first, and second order. Then they want a rate equation out of us. So we've got rate. This is the easy bit. Okay, you got BR minus. You can put to the power of 1, but like it's the same thing, isn't it? It's BR03 minus, I think it was, and then it was H plus squared. Yeah. So then we want to work out the K constant. So to work out the K constant, the rearranged form is this. K equals your rate plus everything else on the bottom, okay? BR3 O minus. If you're like fast, if you're ready, like put it in the answer what you think your K constant is. So I'm going to pick the one that incorporates them all. So I'm going to pick 0.02. I'm going to pick the first experiment. I'm just being weird. I just want to use the first experiment. So I'm going to input the values there. So I've got my rate as 2.52 times 10 to the power minus 4 divided by 0.02, bracket 0.12, and then 0.8 squared. If you put that in the calculator, you should get your K. So guys, what's your K? Perfect. 16.4. Is everyone happy with that? Yeah, cool. Right. How are you guys with units? Do you want to go over through units? Or does anyone want me to explain what the units are? Is that a no for units? Yeah, okay, we'll go over units. Someone's asked. Okay, so I'm going to just rub this off because I need room. So you kind of need to, when you're doing units, you mimic the rate equation. So do you see how we wrote it down here? You're going to mimic this. So if it's something's the rate, you do the units for rate is mole per decimeter s minus 1. Okay, so that's what we do. On the bottom, we have 4, okay? So I'm going to do moles minus 1 decimeters, 6 times by mole. Just you do 4 of them, to be honest, because that's what you've got. 4s come from the fact that 2 of them are first order, and H plus is second order. That's why I've got 4, okay? Moles per decimeters, 3 times by moles per decimeter. 3 minus 1. The way you work it out is you cancel the one on the top, cancel one on the bottom. So you end left with S minus 1, and then you count what's left. So we've got moles minus 3, dm 9, because they've got 9, and then S minus 1. Does that make sense? Cool. That was it. That was a bit of a long-winded one. Okay. So the next one is pretty much the same, but I think because of time-wise, we're already at half past. I think we should move on to a different one, unless you guys want to do maybe a quick Arrhenius equation one. I've got this one. Do you want to do that one? Yes. Okay. You guys hate Arrhenius. Okay. Right. There's things that I want you to remember, okay, with this. Things that I want you to know is this: when you've got Arrhenius, the log form is ln k is equal to minus EA over R times by 1 over T plus ln A. So this is, if you're going to take anything from this, like this session, get that written down in your book. So on a graph, you've got ln K plotted against 1 over T, and typically your gradient is minus EA over R. That's what you need to know. Typically your gradient is minus EA over R, okay? Bless you. It's year 13 content. I would have labeled it AS. So yeah, that's what your gradient is. So in this question, they have given us the gradient as minus 16,000, right? So technically, your EA minus R over R is equal to minus 16,000, isn't it? I would cancel out my signs like that, so you end up with positive both on each side. So then you just solve for EA. Because when I mean by solve for EA, you end up doing EA over R is equal to 16,000. Does everyone know what R is? Is your gas constant? 8.3. Yeah, it's all going to be year 13. Yeah. 8.314, perfect. So you basically know everything at this point, because EA is basically 16,000 times by 8.314. And then what would be the answer? You're going to get a massive number. If we look at our options, if you shout out, yeah, exactly. That's your answer, but it's going to be, that's in joules per mole, isn't it? So you divide by 1,000 and then you get which answer, A, B, C, or D. Okay, so the minus in the signs is because this was negative, because the gradient is negative, and then the answer was also negative. Because they're both negative, they cancel out. That's why you ended them as positive. Cool, perfect. Yeah, well done, everyone. Okay, Right. KP. Right. How are you guys with KP? You like it? Good. I'm thinking, should we get a harder one up? We got a harder one here. No, they're asking me about partial pressures. Okay. I struggle with the temperature on KP. With KP, it you got to think with constants. They always, when you know in the questions where they ask you to tick what is relevant, does it have an effect on the temperature? Constants always have an effect on the temperature. Whenever they say pressure or anything else, then that's when it has an effect. And the normally constants are always, the total of constants is always to 1. So when they say to you when is your constant higher, it means it's a number closer to 1. We'll go, if I find a question on this, I might do another webinar and we can go through that. Okay, so let's do a partial pressures question actually, because I kind of want to go through like an ice. Okay, let's go through this one. It's harder. We're going to go through this one because it's hard. Okay, what do we know? We've got an investigation is carried out on the equilibrium system shown below. 2NO2 gives you N2O4. A sealed flask containing 6 moles of NO2 is heated to a constant temperature and allowed to reach equilibrium. You've got the mixture containing 5.4 moles of NO2 with a total pressure of 5 atmospheres. They want the KP, they want it to 3 significant figures, and they want a KP expression. Okay, so right, first things first, I get out of the way is the easy stuff. So I'm going to write the KP expression first. So we've got 2NO2 is like this. That's our equation, isn't it? So it's products over reactants. Please, 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 for the love of God, right, remember your curve brackets, okay? So you end up doing N2O4 because it's products over like reactants, okay? Squared. Cool. And if you give square brackets, it won't give you the mark. So just be careful. Okay. So we need to actually write down what they've said. They've said a sealed flask contains 6 moles of NO2 and equilibrium mixture contains 5.4. So that they've basically told us what's happened at the start, which is 6 moles for NO2. And at the end, they've ended up with 5.4. So what has been lost is that it's 0.6, right? That's what's been lost during the process, okay? So this is when we need to use the equation, because when you're dealing with moles, you're looking at stoichiometry and you need to know the equation for it. So we need to find the amount of N2O4 moles formed. So if we look at the equation, the ratio is 2 to 1, isn't it, between the products and the reactants? So if I used used up 0.6, that's where I've gone, up for NO2, that means I technically used 0.3 moles of N2O4. You guys happy with that? Okay, cool. Right, you've got basically each of the moles now. So then you want to work out the total moles, which is 5.4, which is at equilibrium, plus what we've used, which is here, and that's 5.7. Then you can do the really nice stuff, which is your partial pressures. Partial pressure is your moles, I'm just going to put M, over the total times by the total pressure, okay? So with that, for NO2, I can do 5.4 over 5.7 times by 5, because that's the total pressure in the question here. That's what you're using. And then you get 4.74 and N2O4. You do it again, N3, 5.7 times by 5, you get 0.263. I think that's what they want. Then we need to work out KP. So you just shove, don't you have to calculate mole fraction? We've basically already worked it out anyway, because that's your mole fraction is essentially the equilibrium moles that we've basically worked out here for total. So we've got KP, we can do 0.263, 0.26, I don't know why it's doing that. 3 over 4.74 squared. Okay. And then you get your Kp is equal to 1.17 times 10 to the power minus 2. And that's your Kp. Yeah, you're right. Well done. And then for units, your units is in atmospheres. So because you've got one at the bottom and one at the top and 2 at the bottom, you just cancel it out and you end up with atmospheres minus 1. Perfect. You guys are good. Well done. Cool. Right. I think you guys are okay with equilibrium. Do you want to do a redox? How are you with redox? Don't get it? I knew this would be the case. Right. Redox. My best tip to you guys for redox is to work backwards. That's why I always tell my students. So let's read it. We've got 0.5 grams of impure NH4VO3 is added to dilute sulfuric acid to form a solution containing aqueous VO2 plus ions. All the VO3 ions are converted to VO2 plus ions. These VO2 ions are reduced to aqueous V2 plus ions by reaction with excess zinc. Okay, right. Kind of put that in one ear and out the other. They're basically explaining the equation to you. With redox equations, there's 2 things you need to take note of. They always give you the equation because you need to use stoichiometry at some point. Okay, so you're going to basically put that to the side for the sec, but the equation is always important. They said the filtrate contains V2 plus ions that is titrated at 0.2 moles per decimeter cubed of solution for acidified KMNO4. You've got the titer of the KMNO4 too, and the ion equation is also here. Okay, calculate the percentage purity. Okay, this is a really hard one. I agree. So we're going to work backwards. First things first is whenever they give you a titer, that's where you're going to look for first. This. Sometimes they get you to work out the titer beforehand and then they ask you to use it, but sometimes they give you an equation and that's what you're going to look for. That's the first thing I always look for in the question, and that's my starting point for a redox, that titer that you can get. Then you need to look, well, they've given you a volume and they've given you a concentration of KMNO4. So if you've got a concentration and the volume, what do you technically have then? Moles, exactly. That's your first point. So if you hate redox, please, at least this is always the first mark in redox. Look for your titer and match it to the concentration. That's your first marking point. Always, always, always. Okay. So I want you guys to give me the moles of KMNO4 now that you know that. You do C times V, but be careful, that's in centimeters cubed and you need to convert into decimeters. 5.886 times 10 to the power minus 4. Fantastic. Okay, that's always your first marking point, okay? Always. I always say to my students, you should be able to get the first 3 points through redox equations because they're always the same. After that, they put some more malarkey in, but at least get the first 3 because it's always the same. Okay, step 2. Always, when you've figured it out, they've given you KMNO4 here. We need to basically go from KMNO4 to V2 plus to the start, because they've said they want the percentage purity. That's why I'm saying work backwards. So we've got KMNO4 moles, but we need to know what V2 plus is. So the way that we're going to use that and find that out is that we need to find it in the equation. And the equation would be this one, okay? Because that's one I'm relating them. So that you're always going to work out 1 moles and try and find out what the other thing's moles is by using the equation. So what's the ratio between V2 plus MnO4? It's 5 to 3, isn't it? So with that, I'm going to work it out. So V2 plus is equal 5 over 3 times by the moles of MnO4. So I'm just going to do 5.886 times 10 to the power minus 4. So you should get your moles as 9.81 times 10 to the power minus 4. Happy with that? Okay, so those are the 2 marks that are pretty much the same in every redox. So make sure you remember them. Okay, step 3, we need to link it back. So we've done this one, we've done this one, we need this now. Okay, so we actually need to link it back to the NH4VO3. Okay, so if we look at NH4VO3, again, it's saying we've got VO3 moles. It exerts VO2, VO2 ion, sorry. So it's this to this. So it's a 1-to-1 ratio, isn't it? So the moles are going to be the same. You with me that? We want the V2 plus because if we're working backwards in the question, because we're working backwards to get to the original, because they're saying that they started with KMNO4, filtered it to a V2, and then went to VO2 from that. That's why we're looking for V2, because we're working backwards. Yeah? No? Okay, cool. Well done. With redox, always work backwards. Okay. So with NH4VO3, they basically said that it's converted to VO2 plus. That's why I got the VO2 plus, and that's why I'm using that. So it's a 5 to, they're both a 1-to-1 ratio because they're both 5. That's why I've ended up getting a 1-to-1 ratio. So there's that. Then that means my moles for NH4VO3 is 9.81 times 10 to the power minus 4 as well. Okay. Those are the 3 marks that will get you the same thing all the time in redox. Now, when I mean why it gets tricky is because normally they change the way that redox is. They'll ask you for the mass, or they ask you for the percentage purity. That's where when I mean the change. But the same 3 marks at the top is always the same. So please remember, look for the titer, link it to the equation and get the next part. And this is different now. Okay, so we need to work out the mass of pure NH4VO3. Now, they gave us the grams, and they've told us it's NH4VO3. So, wait, they've given us a mass that we need in the start, but we've got the moles, and we've also got, they've told us this, so what do we technically have? If we've got an MR, and also the moles. Exactly. So what's the MR, guys, of NH4VO3? Yeah, 117. Yeah. So we do 117 times by 9.87 times 10 to the power minus 4. We get our mass as, I think, let me add it up. Okay, 0.1148 grams. Yeah, it's 1. Sorry, my 7s look like 1s. I'm getting used, and I'm getting confused by them. Sorry. Yeah, so it's 0.1148. Then you've done the maths, you just do the purity now. So we started off with 0.51 grams of impure, and this is what's pure. So you just do 0.1148 divided by 0.151, times that by 100, and then you get your percentage purity. So what's the answer, guys? Cool. Right. That's it. What do you guys think about this now? Okay with redox? Does it make a bit more sense? Oh, I'm happy. Right, well done, guys. Okay, yeah, and we're right. The mark's in there. Okay, cool. Do you want to do another redox, or should we move on? Do you guys want to try another one? Move on? Cool, right, let's go. Acids, bases. We're nearly there. We've got acids, bases, and thermodynamics, and then we're done. Okay, cool. With acids and bases, I'm recording this. It's gonna go on YouTube, so you can watch it back. Is that okay? By the way, have you guys found this quite helpful? I don't know. I presume that you guys like. I'm glad. Thanks, guys. Yeah, I'm gonna do like more free webinars in the future. So, like not so often, but like every now and then when I get a chance, because I'm at uni still. I'm gonna plan to do one, but I don't know. Like you guys just give me ideas. But if you, I don't know. You guys, people hate back titrations. I do a pharmacy degree, and chemistry is my life at this point. So I didn't really do stuff like this at uni, but in first and second year I did organic and practicals. Okay, I can do organic. That is literally what I learned for degrees. So that's fine. But I don't know, who is anyone coming to the boot camp in here? I'm pretty sure some boot camp people are coming. Yeah, it's quite good. So yeah, if you're interesting, like some of the like lessons won't be like this because I've divided it. But what I'm going to do is I'll set you pre-work and homework, and essentially in the lessons we're going to go through questions like this, and it'll be because it's a smaller amount of us, we can speak about it and stuff. And I'll get all the common questions and hard ones and do it together so you can explain. Unfortunately not, but I've tried to make it as cheap as I can. It's like £10 a lesson, so you do 2 hours a week, and it's quite interesting actually. I'm going to give you guys like slides like these, like question packs, and I'm going to give you guys more working as well, so you guys will get a lot. I'm actually excited this week and weekend because I'm going to sort it out. So yeah, I'll talk about the bootcamp at the end anyway, if you guys have any questions. So acids and bases, yes or nay? Yay or nay? Yay? I love acids and bases as well. If you guys are interested in doing pharmacy, it's loads of acids and bases. I had a 20-mark question on it in my end of year. So yeah, okay, cool. Since you guys like acids and bases, why don't you try and do this one yourself, and then I'll go through it. Yeah, I mean I think it's 3 marks. So it's getting harder. Well, you guys have a go at this, and I'll answer some questions while you guys are having a go at this. Okay. Yeah, pharmacy is not as bad as I thought it were. I think it's hard pharmacy is hard now because you graduate as an independent prescriber. So we can prescribe medications now like the way GPs do. So it's harder because they're expecting you to do more. Like for my first year, I was on placement for 4 days. Oh, so I'll answer that. So I was on placement for 4 days, and my OSCE was a day and 3 stations. But now I'm in 4th year. I've just been on placement for a month, and I did 5 weeks in the summer. So in total, I've done 9 weeks of placement, and my OSCE is 3 days. So that's interesting. So it's just hard. It's intense. Like I've come back from placement. I've had like so much exams. It's just intense. I don't think it's hard to understand. It's just like they give you assignments all the time, and it's too much. It's like loads of workload. So I'd probably say that's hard. With pharmacy, so I thought I wanted to do medicine because my sister's a doctor, and my parents was like, why don't you just apply because you're quite like smart. And then I didn't really like the whole process of it. And then I kind of was like, I don't want to do medicine because my old sister she's a surgeon, or she's training to be a surgeon, and I didn't really like the appeal of it. I didn't like dent and opton because it was so niche. And I really liked pharmacy because I heard they were going to graduate as IPs. So I kind of was like, I want to help people, and I don't want to do nursing either. So I also want to be a pharmacist. My last year pharmacy exam, it depends which uni you go to. If you go to a Russell group, they're very like touch and go. Like they expect you to kind of get on with it. But I go to St. George's and combined with Kingston, and they're very, very like spoon feed you. So we get kind of a lot of support. Okay, let's have a look. Right, you're supposed to get, what's the answer? 2.85. Yeah, I'm going to whiz through this one quickly. So this one, whenever they ask you whenever you've got the pH, you technically got your H plus as well. That is just a given, because you can do 10 to the power of pH to get your H plus. That is why. So with this, I'm going to do 10 to the power of minus 9.5 to get 1.12 times 10 to the power minus 2. And then we need to work out Ka. So whenever you have Ka, people get confused which type of Ka. You have H plus A minus over HA, but when you're using mathematically, you need to use the assumption one, where it's Cl, CH2, COOH. Someone put something. And then you sub the numbers in. So we got 1.12 times 10 to the power minus 2 over 0.9. The 0.9 is from here. Oh. And then you put it in the calculator, you get 1.4 times 10 to the power minus 3. Your pKa is related to Ka. That's why we did the whole process. You do minus log to the base 10 of your Ka, which you shove in, and then you get 2.85. So with us as a basis, they're quite easy. You just need to remember your equations. Because one of the things that you need to remember for your syllabus is that you have to remember the assumptions that your ratio between your H plus and your A minus is a 1-to-1 ratio. And that's why you have to assume when you're doing maths that is H plus squared. So that's actually one of the questions they could ask you. What is one of the assumptions of the Ka formula? And you need to remember that H plus and A minus is a 1-to-1 ratio, and therefore we can actually use it in the equation like this instead. That's okay. Cool. Make sure you remember that because it could ask you it. Cool. Yeah, we got that right. Let's do a buffer. What about this one? Do you want to do this one, or do you want a buffer? Buffer? Do you want me to go through this one with you? Okay, let's do this one. Oh, okay. So for this one, it's really, really, really tricky. So, but don't get thrown off by it. Make sure that you kind of fixate on the easier stuff that you do know. So with this one, I'd zoom in straight on pH because pH is your friend and it's the easiest thing to do. Because if you have pH, again, you technically have H plus. So you can do 10 to the power of minus 5.07. And then you can do that to get, if I put that in the calculator, that would help. Minus 5.07. You end up getting 8.51 times 10 to the power minus 6. Happy with that? Cool. Right, I think you guys are easy with that. Then I'm going to work out what I actually know. So we've got 3.36 grams of KaOH. And we only really work with moles, don't we? Or moles per decimeter in some sort of capacity. So I want to get that grams into some sort of moles. So we have KaOH and 3.3 grams, right? I want you guys to be able, give me the MR. No, not the MR, the moles for KaOH, please. Yeah. Yeah, 0.06. Cool. Well done. Okay. So, have you guys heard of the Henderson-Hasselbalch equation? Have you heard of that? Right. So, they have put it in your spec. You should essentially know it, but it's a very, very, if you're doing a buffer question, you want to know the Henderson-Hasselbalch equation, okay? It's a lifesaver. So I'm going to give you guys it. So the Henderson-Hasselbalch equation is pH equals pKa plus log of your A minus and your over your HA. Get that written down. That's called the Henderson, I think I've spelled it wrong, Hasselbalch. And that is for buffers. It's the easiest way to work out a buffer into, like, I think that's my best advice. Equations are better. Okay, everyone got that down? Cool, right. Yeah, you should both know both of them for examples. If not, I learned this in degree as well, so it will be an easier way to learn it. Like, for example, I don't do Hess cycles, I hate them, so I just do an equation that I remember and it works anyway. So yeah, this is probably an easier way. If you don't like buffers, this is a very good way to use the Henderson Hasselbalch. So we worked out the moles of KOH. We worked out, so KOH you guys said was 0.06, okay? We need to work out the moles for the acid now, because they've told us that we've got 0.376, okay? And we've got 250 centimeters cubed. So what's the moles for the butanoic acid? Covering it, that would help. Okay, 0.94, right? I'm happy with that. Cool. So I'm just going to put but is 0.094. Okay. Cool. Right, it's technically in this step, what they're basically saying to you is that some sort of neutralizations occurred, hasn't it? Which means that we need to essentially work out how much acid is actually left from what we actually used. What I mean by that is you're going to do 0.094 minus 0.065, because the reason why I'm saying you have to subtract them is because they reacted, it's dissolved. So you need to work out essentially what is left. So with that, you should get 0.0335. So, and that is basically your conjugate base in this case. So with that, using the equations which I have essentially, your A minus is going to be your 0.0605. Your HA is going to be your 0.0335. Okay? Because a reaction occurred, and that's what your HAs are going to be left. So if we divide them, you should get 1.81. Where's the 0.00005 from? Where's that from? Have I wrote that where? Where? You mean this one? Because they reacted. You need to subtract them to see what's left. Oh, well, that's why I wouldn't add. I know you're saying they're dissolved, but it becomes part of one. So your mass is not going to be added. It's going to be technically say the same, and you're going to essentially lose something. So that's why I've subtracted. And yeah. Darshan, what do you mean by 0.005? Are you happy with moving on, or do you want me to answer anything? 0.09 minus. Yeah. You're making me stress. It's rounded though, right? I've just rounded. Oh, you can have that. That's being really picky, mate. No, so you've worked out this part. Okay? No, don't worry. All right, so we're going to shove it in the Henderson Hasselbalch now, because our pH is 5.07. Sorry, bear with me. Equals pKa plus log, and then you know that it's 1.81 now in brackets. So if you do that, you should technically get your pKa is equal to 5.07 minus 0.258. I think when you put it, that you do the log to the base 10 of the 1.81. Someone's message. Yes, exactly. You're doing neutralization, so it's the exact same kind of thing. Yeah, good. So when you subtract them, you should get 5.07 times, no, delete minus 0.258. 4.812. So I've got the pKa, so what can I work out then? Can you guys give me the Ka? There you go. So A minus is your salt, which we know this is a salt, isn't it? Potassium hydroxide is your salt, and HA is your overall acid. That's why I put that one as A minus, and that at my difference. Your H plus, this is your H plus, but that's why I subtracted them because I need to work out my HA, and that's why I did that. Did you explain that again, Kanisha? I know it's really hard because yeah, happy, cool, I'm happy. Right, we're running out of time, so I'm gonna end it there. But did you guys? And they're like I didn't really help myself. I picked the worst questions, but I wanted to pick hard ones because I wanted you guys to get an idea of how to do them. So I want to answer some questions because we're ending up because I wanted to. The whole point of the webinar is to kind of introduce you to the bootcamp. Bootcamp. To join the bootcamp, it starts next week, so the deadline is to join tomorrow. So if you're interested, I'm going to quickly talk to you about how to essentially. I'm going to end the call this way.